So I'm really wondering how values that are not exact are pointless, but so feel free to explain.
Well,
Wow, that was an introduction. Who's that for?
What was that? What I wrote, by the way. Let us go through that.
Can we
Okay.
can you briefly outline it for anybody that hasn't got a fucking clue what you're talking about? Please.
Okay, so basically what I said was that you can use Newtonian gravity to calculate the motion of basically any number of bodies with arbitrary precision. Well, it will never be exact, but by setting the simulation step size to small enough values, you can get basically any precision you want. And WhatsApp said that if it's not exact, then the calculations are pointless. So that's pretty funny to me, because
Okay, so when you say Newtonian gravity, what's that? Is that the one that acts perpendicularly?
If I only knew what would happen, but okay.
Newtonian gravity, basically the theory of Newton where the force of gravity is...
yeah, I know, but I'm just interested in the vector, like what it is, right? I don't need to know the concepts of what other people think. Is that the one that acts perpendicularly to the surface?
Not necessarily. Basically, well, usually, but not necessarily, because, well, you can have surface that is not perpendicular to the force of gravity, that's no problem. Well, you have, like, mountains or something like that where you have slopes, so that's no problem.
Okay, so that it acts perpendicularly to what? What's it act perpendicularly to then?
Basically, if you have any 2 point masses, then it acts on along the line that's connecting the point masses. That's it.
And the line that's perpendicular to that vector is the line that it's perpendicular to.
Perpendicular to what? Because I think we're kind of veering really off topic right now.
Is it vertical? Is that basically what we're
that's
talking
what I refer
about?
to, by the way.
A plumb bob. Newtonian gravity. Is that what Newtonian gravity is? Like the effects that we all see on a daily basis shown by a plumb bob. Would that be Newtonian gravity?
That would be kind of conflating the description with the effect. The effect can be described by Newtonian gravity. Let's just put it this way.
Is that effect a vector that we call vertical?
It can be described with one. I
What
wouldn't say
you would like to just swap and change your description whenever you feel like it, right? You leave it open-ended. So it's not exactly exact. It's sort of variable exact. Whenever you want it to be exact, it's whatever you want it to be, right? That Newtonian gravity.
I have no idea what you're talking about right now.
I'm trying to get you to say what it is that you're talking about, because you're talking about a notion of something, right?
I'm talking about a mathematical construct that is Newtonian theory of gravity, which can be used as a description of the phenomena that happen in reality, but is not reality, as no theory is reality. Don't confuse the map with the territory.
Can you talk about what happens in reality then? Because when you talk about what happens in your imagination...
Like something that I wrote, by the way, in the chat. Science it out. Like, I don't know, half an hour ago.
What exactly?
What you just said.
What, that description is not reality? I think I never really argued with that.
Exactly what I wrote.
But when we're talking about reality, we're also using words, and these words are not reality.
This, seems like, because people seem to forget everything within 5 minutes, but I just posted it. Again.
Okay.
What is the second point that I made right there?
Okay, so should I read it? The value is coming from this one, you mean?
The value is coming from a very basic dumbed-down formula that certainly doesn't concern reality whatsoever, since we rule out everything we don't need. Right? And then I explained
Well,
that
depends on
what we
what.
don't need is actually equals to, especially in physics, by the way, especially in theoretical physics, it means that we don't like something because it would fuck up everything that we are trying to promote as our scientific field.
I think you're kind of confusing a few things here, because of course
Tell me
if
what.
there is a theory, then usually the theory only concerns like some particular effects and not everything. I mean, we still don't have a theory of everything. And in order to calculate any
No, sorry,
practical result,
you
we
just
have
said a
to.
very big thing, because the theory of everything should be explaining in one equation everything that happens at the same time. That's not any
Yeah, pretty
scientific
much. That's
field's goal to achieve. Every scientific field exists separately from each other because they are trying to show their own view of the world.
not quite. I wouldn't put it like that.
Well, that's what's happening. Especially, for example, in formulas that, is describing Newtonian gravity.
Okay, so in theory, you should be able to kind of use, for example, quantum mechanics to describe how a
Newtonian
human body
gravity? No,
works.
sorry, the
But
Newtonian gravitational acceleration doesn't include anything regarding that. Nothing.
of course, yeah, it doesn't, obviously. Yeah.
That's what we were talking
So,
about, so I'm trying to deviate back to the original topic, what you came in here for, I think. So, what was the second thing that I wanted to say? Yeah, you said that it's very funny that I wrote what I wrote. Like, what do you mean by that? Why is it funny that I'm telling you that if you cannot get an exact, then you shouldn't calculate anything?
basically because you just said that the whole of science is pointless, and well, that we can't really know anything if we don't know it exactly, and that's a bit silly because, well, all of science and all of
What was your
technology is
analogy?
built on results that are not exact.
Yeah, what was your analogy?
Yeah, my analogy was with the distance between two places. I just picked London and Paris randomly
Yeah.
and just took the distance from Google Maps and said, okay, so that's an approximate distance, and apparently it's pointless to talk about it if it's not known exactly.
Yeah, what do we use that information for? When you tell something
Traveling,
like that to me?
let's say.
Yeah, well, not really, by the way, because for traveling I don't need the distance, I need the vehicle, or I need the route, or the path that I have to take. So
Well,
you're not
yeah,
even
but
right
the
about that,
distance
by the way.
between. Okay, but the distance between two places is a good first approximation for the length of the route. But of course,
The
you
length
can
of the
then
route.
divide
That's fine, yeah.
the route
If you
into
phrase it
smaller
that way,
intervals, and yeah.
it's kind of fine, because even then I could take very different routes that will take very different time to get from A to B,
Yeah.
right?
Yeah,
So even
sure,
that,
but none of
is
them will be
not,
exact.
not exactly correct to say something like what you just said, but okay, let's move on to the real problem with this analogy. That what do you use when you say 340 kilometers?
What do you mean?
What did you use to determine that value that you came up with?
Okay, I just used the map, Google Maps to
Exactly.
be exact.
Yeah. And what did you want to achieve by telling me that? Like telling that to someone, anytime. What do you want to achieve with that?
Just basically saying an example value that is useful, because it would be useful to, for example, approximate the amount of fuel I need to go from London to
Yeah.
Paris.
Fuel.
But it's not exact.
Okay. Again, since it's not exact, how do you know the fuel at all?
I know it approximately. So I know, let's say that my car burns like, say, I don't know, 8 liters of fuel per 100 kilometers, and this is 340 kilometers.
It's just an average.
Okay,
That is
yeah,
based on
sure.
the average speed. So
Of
if
course,
I go through a path in which I cannot get to the average speed, but I'm way below it or way above it for most of the time, then I will get a very different value for the end of how much fuel I need. So that's not true even. But what I'm gonna get at is that you used in that analogy a map on which you pointed out for yourself 2 points wherever, And the map told you that how much is the distance in between those 2 points. Great, but when you are talking about in physics, some theory, and that theory has some formula regarding how should something move, then you are talking about exact numbers based upon each other and then using them and then coming up with an end value for something, right?
Kind of, let's say. Okay,
So,
where are you going with that?
Was that a right analogy to actually get together something that you say that is a map, that you use your fingers and your mouse to point at 2 points, to make an analogy with that, with mathematics, which is exact always?
Well, actually, what I used, the map, is also executing some kind of maths in the background. So basically, regarding the distance.
No, you didn't. You pointed to points that you
of course, yeah. I pointed to 2 points, and the program told me what the distance should be between these 2 points. So basically, it executed some calculations because it doesn't have like a database of all possible pairs of points on the map and the distances between them. What it has is some specific model of the shape of the Earth and of basically where everything on that model is, and then it tells me the calculations based on that model. So basically it told me the distance between those 2 specified points as predicted by that model, and this is some kind of a number, and it's not an exact number. So by the logic that you said, it should be pointless to even show me that number because it's not exact.
Yeah, exactly. I just pointed out why you shouldn't use something like that, for example, for determining how many fuel you need. That's really pointless, by the way. That's fucking pointless, because you can come up with very different stops for your route when you take it.
Of course.
If you miscalculate it. So you can end up in the middle of nowhere, literally, just because of that.
So that's where I don't agree, because just because you don't know how much fuel you will use exactly,
is that you don't let me finish, do you?
Okay.
What I wanted to point out is that you are comparing two very different things, that one should be very exact because it's based only within mathematics, but the other one is basing on you pointing out something on a map, like arbitrary, just like choosing it because I like that exact point, and then the other exact point. You don't even think about it, you just point it wherever you want to. You're comparing the two. Is that what science is to you?
That's kind of quite similar, actually, because every time you're doing any calculations in science, you have to input some values that are coming from measurements, and they will not be exact. So, by extension, any calculations you do on these values will not be exact. I mean, you can have exact results based assuming the values are exact, but the values are not exact, so the results will also be some approximation.
Please rephrase it, because that didn't make any fucking sense.
Okay. You can have some... Okay, so let's say you have some equation, you put in values, and you get some values as an outcome, right? So then, if the values you put in were exact, then the result would... the result will exactly correspond to the values that you input in the equation, right? But the problem is, the values that you input into the equation do not ever exactly correspond to reality. There is always some uncertainty, which means that the result you get from the equation will also have some uncertainty when you try to basically somehow refer it to reality, right?
Okay, regarding the Newtonian gravitational acceleration, what do you mean by not exact? What do we not put in correctly?
But I think we kind of just, because that's not where I was going with this, really.
What, so maybe let me... we were talking about in the first place.
Okay, but maybe let me now finish, and maybe it will become clear what I meant. So in the case of the map, I put in, let's say I lived in London. I don't live in London, in case that's not clear, but let's say I lived in London and I wanted to go to Paris. I choose 2 points on the map, one in London, one in Paris, and I used it to estimate not to calculate exactly, but to estimate how much fuel I will need. And of course, then I know I will have to take some margin of error and probably get a bit more fuel in order to be sure that I don't run out of it somewhere on the way. But basically, I'm using it to estimate. But even if I had some very precise model of my car's fuel consumption, and I knew very precisely what route I will take and where I will stop on the way, etc., etc., even with it, the values that I would put into, let's say, Google Maps when I would choose the starting point and the ending point, they won't be exact ever. So even if I had a very, very precise model of everything and I could do exact calculations having some input, even the result of these exact calculations wouldn't basically be the exact consumption of fuel that I would get on my way from London to Paris.
Yeah.
And it's very similar because, so now next step, if we have two bodies in Newtonian mechanics, right?
That's another topic. Let me rephrase what you, not rephrase, but react to what you just said, because that's another topic, right? Okay, so no one does what you just described, ever. No one does it, okay? No one does it.
What do you mean?
Do you know what people actually do when they want to travel very far away?
Yeah, they pretty much refuel on the way whenever they are close to running out, unless.
So do they do?
Unless they are traveling. Usually not.
Usually, never. Like,
not
be
quite.
a man.
Actually,
nobody does that. Okay, nobody does that.
And here I disagree because I've done something like that a few times. Well, not very exact calculations, but for example, sometimes it is of interest to me whether I will have to refuel on the way, because that changes the time I will take to get from A to B.
Yeah, and since then, for example, if I have since you know because you just described yourself that even if you put in everything that you couldn't come up with the right answer, then you wouldn't do it that either. I mean, you shouldn't.
I won't have an exact answer, but I will have. Well, for example, if I know, okay, look,
right.
if I know that I have fuel that will last me for 500 kilometers plus minus 50, let's say, because that's a reasonable margin for error, and I have only 200 kilometers to travel, then I know that it will be enough. I don't know how much exactly I will burn on the way. I don't know how much fuel exactly I would have to take with me in order to basically get from A to B on exactly the fuel I took. I don't know that.
That's a factor of 2 times. That's a factor of the error of 2 times. Is gravity like 19.2 meter per second squared?
That's not what I'm trying to say.
Then, because you are literally comparing that to the actual science right now. And how they do things. That's why I'm
just saying what I'm just illustrating what the margin of error is.
It's a factor of
so
2,
basically
2 times error.
Not a factor
that you just
with gravity. With gravity, it's not a factor of 2. It's much smaller. But still, there is some margin.
Then maybe don't compare the two next time.
Why not? The idea is the same. The numbers are different.
The numbers are hugely different. Because if let's
but
say
the idea is still the
gravitational force would be 19.2, it would be very different, wouldn't it? The whole of the matter altogether.
Yes, of course. But the point is, still, we have some values known with some accuracy. They are never exact. Of course, the ratio of accuracy to the number is much different, but the idea is the same. We still know that the value we measure will be between this and that. We only know the range. We never know the exact value.
Yeah, sure. But that's why I wrote that either you are having a very flawed analogy and you are laughing about it, which I don't understand in the first place, or you literally are destroying the scientific field, because if you can have those kind of errors, then you got nothing. If you allow your science to be that far off, then you got nothing.
It depends. I mean, sometimes people start with models that are far off, and then they are refining it to get more and more accurate. Basically, that's almost what happened in the history of science. I mean, the first models for, let's say, predicting celestial events
when was the Newtonian gravity first established? the value for
like
it?
17th century, something like that.
As I know, it's the same that I know, yeah. Did it change since then?
Newtonian gravity.
Uh-huh.
The
value,
basis? No, the basis.
The value for the Newtonian gravitational acceleration. That's what I'm asking. I just try to be, not take up as much time as you sometimes like, because you like sophistry. I do not. I get to the point. So, did it change?
Okay, what do you mean by the value for the Newtonian gravitational acceleration? You mean the Earth's
You just said
gravity?
that it happens all the time in science. Did it change throughout the history since it was discovered or established?
Okay, but what value do you mean? Because there isn't a single value that can be called Newtonian gravitational acceleration.
No, there is not.
No, there is not. I think you mean
so
Earth's
you won't
surface
answer
gravity.
to the simple question. Okay.
I think you mean gravitational acceleration on the surface of the Earth, with so the 9.81, right?
Yeah.
Okay.
Yeah.
So, and then again, another question: what do you mean by did it change? Did the value itself change? Or did the acceleration itself change, or did the measured value of the acceleration change?
The value. I asked for if the value of that changed.
Because I'm pretty sure that the measured value of the acceleration did actually change throughout history.
By how much?
I don't know, probably a few percent at most, because it's quite easy to measure precisely, but I don't know.
What do you mean by few percent? That could mean anything for anybody when you say it like that.
Well, if you have the 9.8, right, then 1% out of it is 0.098,
so one,
right?
By few,
that would be 1%. So if
1%, okay.
No, I don't know if 1%. Of course not.
Okay, because you were analogizing the whole of this to the whole of what you were talking about when you were talking about having 500 kilometer equivalent of fuel.
There are actually... Right? Okay, so... But there are actually values in science that have changed by more than a few 100% throughout history.
Which value?
For example, and now let me just think what would be a good example.
I can tell you one, like right off the top of my head, like literally, but
okay.
Do you want me to help you out a little bit?
If you want.
Okay, age of the universe.
Yeah, that's actually a good example, I guess.
Yeah, can you show me any mathematical formula that was used ever to determine the age of the universe? Especially back in the, let's say, 1600s.
Back in the 1600s, I think they were basing it more on the Bible than anything else.
No, they were not.
Because they didn't even... I don't think they even thought that the universe is something much larger than the solar system, but
no, yeah, they were not.
I don't know. I don't know of any really value for the age of the universe from 1600s.
Not value, I'm asking for a formula. So I'm asking for what comes before the value that they come up with at the end.
Okay, I have no idea what they could use for the age of the universe in the 1600s, if they even had any.
Theory that you could tell me regarding that.
If you are asking still about the 1600s, then I can tell you that because I have no idea if they even had something like that back then.
Okay, do they have something today for the age of the universe? As a formula?
Yeah, pretty much.
As a formula, yeah.
As a formula, well, the
closest... So where does it come from? Where does that 4.5 billion comes from in the first place?
4.5 billion is not the age of the universe, but the age of the Earth.
The age of the Earth, yeah. That's why I said, for example, because it's a smaller number. I'm giving you some hand, to give me some formula for the age of the Earth. Do you know that?
So, yeah, so that one would come from probably, but here it's kind of an educated guess. I'm not 100% sure, but I think that they are mostly basing it on how is it called? in English, like radioactive dating, something like that. So basically checking the proportions of radioactive elements in the rocks and figuring out what the proportion should have been.
That doesn't go for millions of years.
Long time ago.
I think not even for millions of years. So
if you mean carbon dating, then not. But there are different elements.
That's 57,000 years. That I know from the top of my head.
I think that's for carbon dating, but there are different radioactive elements as well, like uranium, for example, which has a half-life measured in billions of years. So I think that's mostly what has been used to determine that. But I'm not a geologist, so that's only an educated guess. I can't tell you with certainty.
So again, what did I ask for? Like 20 seconds.
You asked for a formula, but then basically you would have to take the formula for how the half-life affects the ratio of an element and the product of its decay, and then rearrange that so that you can input the current ratio and get the age of the sample, which I won't be able to do on the fly. I would have to take a few minutes at least to rearrange the stuff, but basically you could use that.
Well, by the way, for example, what you were talking about, the half-life of uranium. How do you know that? What is the half-life of uranium isotope?
You basically take a sample and you see how quickly it decays, and actually it's quite easy to measure because you don't have to watch the sample for a time that's even comparable to the half-life. Because when you have a sample that has a large number of atoms of the substance, then you can basically watch how often do you get a decay, which can be also measured quite precisely with things like Geiger counters, which are almost able to detect every single decay event. You basically get a click out of the counter every time a charged particle enters the detector.
Geiger counter is what? Sorry. A Geiger counter is used for what?
Basically detecting radiation.
Okay, we're talking about some numbers. I don't get it, but okay.
Okay, so yeah, with a Geiger counter you can measure how much decay events you get per unit of time. Yep. And when you know how many decays you get per unit of time, and you know how much of the substance you have in the sample, you can basically use these values to calculate half-life.
Sure, so Geiger counter gives you particles, how much particle has left the specimen that you are using it for. I didn't know about that, but okay.
Yeah, pretty much.
Wow, okay. So, again, back to the basic idea we were talking about, what? The gravitational acceleration, right? And the basic formula that you certainly do believe in, right?
Okay. So what's the question now?
Oh my fuck. There's no question. That was my basic claim, and then I'm waiting for you to say okay or not, or can we go on from that?
Okay, so sorry, maybe I didn't hear what you said. So could you repeat?
Yeah, sure. So you claim that well, I guess you are claiming. Let me be clear about that. I cannot know, of course, but I guess you are claiming that the basic gravitational acceleration formula is correct by itself.
Okay, which formula are you referring to right now?
The F equals m1 times m2 over, what is it? Fuck.
R squared, yeah.
Distance. R squared,
yeah. And times the gravitational constant, yep.
Yeah.
Okay.
So what does a formula like that, for example, tell you? What does it show?
Basically the gravitational force between 2 point masses.
Yeah, what else does it show?
You will have to tell me what you're referring, what you're getting at, because I have
My point is that it shows you nothing else.
Okay, yeah, that's fair enough.
So how does it refer to reality whatsoever?
Basically, it only describes one of the aspects of reality and not the whole reality.
Which aspect?
the gravity, basically.
So there are no other forces that would act upon a mass.
Usually there are, but
usually when there
it's...
is not, because you are being very vague at certain points when you are talking, and sorry, I cannot take it. When does it when it doesn't? When does it happen that it's only gravitational force that happens?
Let me put it this way. If you had a perfectly isolated mass, like perfectly isolated from any external influence like electromagnetic, etc., shielded from any particles in perfect vacuum, etc., then you probably theoretically could have a mass that only interacts gravitationally, but in practice it's undoable. So yeah, in practice you won't ever have a mass. In practice it's pretty much not doable.
Not doable. What do you mean by that?
Yeah. So you won't ever be able to perfectly isolate a mass in a perfect vacuum and etc. So always you will have some kind of other
that requires that. What does a formula that requires that imply to you?
But it doesn't require that. It just tells you one of the forces, how to calculate one of the forces that act upon a mass, and if other forces. Okay, but it tells you how to calculate it while one part of what acts upon the mass, and if other things are negligible, then that can be good enough to make some quantitative predictions.
Negligible? When does something become negligible?
It depends. It depends on what your application is, basically. Because...
yeah, I have to go back again to what I wrote, like now for... almost an hour ago, right? Dumb formula that certainly doesn't concern reality whatsoever, because if it would, then it would fuck up everything. And what did I wrote in between those two thoughts? That you rule out everything that you don't need. How do you do that in real life?
In a way you do. In real life you can't ever rule out everything, you can just attempt to, and basically then you take the influence of all the other factors that you can't rule out as uncertainty. That's basically what you do. Only practical approach that's possible.
Uncertainty of what?
Uncertainty of the measurement of the result of things like that.
So the result itself is uncertain.
Yeah, usually.
Then why do you do the calculation in the first place?
Because sometimes the uncertainty is small enough that the result still tells me something.
No. Uncertainty is not a value whatsoever. It's just an adjective that we use to describe something that we cannot be certain about, right?
Not in the case of experimental science. In experimental science, uncertainty is basically the value, the margin of error that you have on the value that you measure or on the result of calculations.
It's not margin of error. It's not uncertainty whatsoever, especially in physics. You don't use that kind of phrasing and equal the two. No.
Maybe I'm just using...
It's either margin of error or uncertainty. Sorry. Those are two very different things, especially in the field of physics. Those are very two different things.
Okay, maybe I'm just directly translating from my native language. That might happen. Because in my language, if you use the word for uncertainty, it's often used as referring to the value that you basically have, like a plus minus b, then the b is the uncertainty of a.
Oh, okay, sure. It must be your language then. So, again, if you don't have the value that is coming from reality, then what are you calculating in the first place?
Give me a moment, because
okay.
Okay, I don't think it's actually the language thing, because
me neither,
if you just Google...
I give you that, no problem.
If you Google measurement uncertainty, you basically get that in metrology, measurement uncertainty is the expression of the statistical dispersion of the values attributed to a measured quantity.
Okay, can we move on to the real thing that we were talking about? Okay. Should I ask it again?
Yeah, sure, because I was
so
just checking if I...
Yeah, if your input value is coming from not reality, right? then what are you even calculating in the first place?
But the input values usually come from reality.
Oh, they do.
If not, then it's just an exercise in calculation mostly.
Didn't we just establish that a certain requirement for having in reality a formula for two masses having an attraction towards each other would require to every other force not to be present whatsoever?
No,
You
think so.
You didn't? Oh.
No, I just said that you will never have a situation, but well, you asked me if I will ever have a situation where every other factor is excluded, and I agreed that no, we won't, but that doesn't mean the formula is useless. Just, I don't know, it's...
Yeah, so what do you use it for? That's what I'm asking. That's
example.
also what I asked, by the way. What do you use it? What are you calculating when you are calculating that, for example?
Basically, the gravitational force between two masses.
Great, and what do you use that for?
Depends. You can use it, for example, for predicting celestial events, because you can use that value to.
Fuck.
Yeah, you can use that. You can use this this formula to simulate how objects in the solar system move, and then predict things like eclipses.
The eclipses were not predicted regarding any sort of gravitational acceleration formula whatsoever. And you know
Initially, no. Initially, maybe, but currently they are being predicted using that. The precision that is currently achievable is thanks to the theory of gravity.
And no, it's not.
Yes, it is.
And though it was precise even when the Mayans came up with
their...
yeah?
Not to the second, and not and you didn't have the locations known so precisely.
Oh my fuck, okay. So, again, when you are calculating two masses having one force, then you are talking about reality as if reality only consisted out of those things. So when does it ever happen?
Not really.
That's why I'm asking.
But we don't talk about reality as if it only consisted of these things. It just means that we are only considering this aspect of reality right now. We know that there are other aspects and that they may or may not be significant factors, but we are just considering this single aspect. It's just the way you make this, I don't know, how do I put it?
Yeah, very good. Did you hear yourself what you said in the very first sentence?
Okay, what did I say that got your attention?
That it should have anybody's attention, especially when you are talking about physics. I hope you are not talking for physics whatsoever, but you said that you are not talking about reality.
No, I don't think I said that.
Listen back to it some way, but that's what you said. You are talking about reality as if reality only consisted out of those things.
We don't talk about reality as if it only consisted of these things. We don't talk about reality.
And you are very right about that. You cannot talk about reality as if only two masses were in existence, having only one force in between them, acting upon each other or having an effect on each other. That's fucked up, and you're right about that. When you said that, you were very right.
That's an aspect. That's a part of reality. You can talk about it as basically one of the things that are happening. You will never, well, even if we're talking about, I don't know, it's as if you required of me that when I don't know, when we're standing somewhere and we're watching cars go by on the road, and I said, oh look, a blue car just passed us, and then you raise the fact that I didn't take into account the fact that the car was not only blue, but its make, its brand, basically if it was a diesel or a gasoline engine, and I didn't take into account all the other cars on the road. I didn't take the weather into account,
I get it,
etc.
Yeah, I get it. That's why exactly I asked you 5 minutes ago, what do you use the gravitational force for? Because when I tell you, for example, that car is blue and it just passed by us, I'm maybe trying to make a joke about it or something like that, right? That's what I'm using that information for. What do you use? or anybody by the way, uses the gravitational force for?
Making all kinds of predictions, like the eclipses. That's what I said before. I think we're kind
back
of
to the
coming
eclipses
back.
that we should dismiss altogether, because it was way before described than anybody came up with any Newtonian gravity. So
yeah, they were able to predict eclipses with some accuracy, but the accuracy that is achievable right now is thanks to gravity. Or okay, but if you don't want eclipses, sure, basically any other kind of motion in the solar system. If you have the motion of planets and predictions where the planets will be in the sky at what moment, if you fire stellarium, for example, and then look at what the sky will look like at any given day, that's basically in its core based on the Newtonian theory of gravity. Actually, even some Einsteinian corrections are in there, I believe, because the ephemerides for the planets aren't precise enough if you don't take into account some relativistic effects. So that's also interesting, actually.
Okay, sure, great. When you said eclipses, you were talking about the sky, and right now you are talking about the sky. So do you have anything else that we are using the gravitational force for on the ground?
On the ground, we will be usually using an approximation that is simpler, because basically if...
approximation of what? Sorry.
Approximation of the formula for gravity. So basically, if you're working with stuff on the ground, like, I don't know, if you want to throw a ball and calculate how far it will land, or I don't know, shoot a bullet and calculate how fast it will drop along its path, then you will usually just use the value for gravitational acceleration, right? The Earth's gravity, and you will not do the whole calculation based on Newtonian gravity. You will just
it's a movement.
Instead of using gm divided by r squared, you will just use small g and get on with that.
Yeah, great. That's a movement we are talking about.
Because usually you just don't need the level of detail that the full Newtonian gravity provides, mostly. In theory, you could still calculate, yeah. Because, for example, if you say that, let's say you throw a ball, right? And if you learn about how to calculate the trajectory of a thrown ball at school, and you use basically use small g. Yes, I have actually.
Cool. What did you experience regarding what makes the most difference in between two or many different shots when you are doing that? What makes the actual difference in between very different shots?
But when I'm throwing? Mostly the way I throw it. Because I cannot do... Well, I cannot throw a ball in a very repeatable way.
Yeah.
Well, in different throws, I will throw the ball with different velocity at different angles, so every time the throw will be different.
So you affect it with a different kind of force, right? That we can call, let's say, pushing, like fast pushing, right? And then we can talk about what else.
Okay, let's say.
Does anything else come to your mind regarding?
You're probably referring to air resistance, right?
No. Well, it's part of it, by the way, but that's not the main point of what I'm trying to get at.
No, okay, so I don't know what is the point.
It's the motion of your fingers as they leave the ball. It has a and baseball players will tell you that has a very big effect on how and which kind of trajectory the ball will have on its path.
Yeah, probably. Fair enough.
Like, it could literally go from, let's say, one shot going north, and then the next one going east, like almost directly towards east, having a curved path on its way, and then the other one, the third one, going to the west. So that is what we call empiricism, right? Because we went out and we did something in real life, and then we realized that it's certainly not just the fucking gravitational force that is affecting the ball.
Of course, nobody ever says that in practice. It is
So
always
what do you use
just
the
a single
gravitational
factor.
force for in that example?
Okay, if you want to predict the flight, well, predict, or maybe predict is not the right word because it is hard to predict how exactly a person will throw a ball, and you would need to know exactly, well, you would need, exactly, maybe it's not the right word again, and you will probably pick on it later, but you would need to know with good accuracy how the ball is rotating when it leaves the hand of the person, and what is the velocity, what is the angle, stuff like that, which usually you won't be able to measure. But for example, if you have a machine that will launch a ball into the air, it can with a machine you can control the parameters much more accurately, and you can get much more repeatable, let's say, throws, even though maybe it's not the fully
I'm not
right
talking
word
about
here.
machines and how to make a machine, because that machine is, by
Okay,
the way,
but that's
made by having like some kind of rotary system that tries to spin at the same speed all the time. That's it.
okay.
We are
Cool.
talking about
Not the point.
formulas. Formulas regarding reality.
Okay. But the point is, when you have something that can launch a ball in a repeatable way, so that every time the launch will be the same, or at least approximately the same, then you can use gravity along with some additional formulas, of course, because it's the additional effects are also
So
important.
you think that they,
But
when they made those devices, they used the formula of the Newtonian gravitational force?
Not directly.
Then how?
No, because they didn't have to. They
So they
probably
didn't.
just used the value
Okay.
for small g. Yeah.
Because again, you just did what you did before, and I asked you not to do. You said that not directly they didn't use, and then right after that you said no, they didn't use. So either they did or they didn't. Like, make a choice. What you wanna go with? So
Okay,
did they use
probably
it or
they
not?
didn't. If you want to go this way, then probably they didn't, because
No, I'm certain that they
for
didn't.
stuff on
So
yeah, because that's not, as I said, you don't require this level of precision. They could have used it just as well, and they would get the same results basically. But that's the point. It's more complicated, and the results are the same. Well, there
how could
will
they
be a difference, but on some faraway decimal place, which is not important at all.
how could they get the same results when they weren't even calculating anything in the first place when they were doing that shit? Like literally making the device wasn't they didn't nobody thinks about that kind of thing. That's what I'm trying to get at. Nobody uses the gravitational force formula for anything regarding reality when they are doing
That
and making
is
something.
completely not true. Okay,
Did you hear
first
what I
example,
said?
do you know? Yeah, you said nobody's doing that, which is not true.
Nobody is doing that when they are trying to make something. That's why I asked you, did you hear what I said? You didn't. Or you're trying to
Yeah, and
misrepresent what I said 5 seconds ago, which is just stupid. You can do
that
it,
is
but
still not true, because I can give you just a very simple example. Well, simple. It's just the first example that came to my
okay.
mind. But there is this YouTube channel called Stuff Made Here, and I don't know if you've heard about it. And the guy from this channel made things like self-aiming bow, for example, or I think he did something with basketball throws.
So you may
have to check him out again. But basically, he was doing things that involve throwing or shooting arrows or stuff like that, and where the aim was well, a perfect aim was the primary goal. And I can assure you that he did use the gravity, well, at least the small g in his calculations when he was designing the machines that he was building.
You can assure
Because
me.
otherwise he just wouldn't be able to achieve what he achieved.
You can assure me that he, for example, used.
Yeah,
You
if
can show it.
you can. Okay, you can ask him directly. He has a YouTube
What?
channel. He has. Just ask him directly
Mate,
if he used it.
Either you have something or you don't. Don't tell me where to go and whom to ask and whom to talk to. Like, either you have something or you don't. Like, this is what I told you, I don't know, 40 minutes ago. Be a man. Do you have something or you don't? If you don't, then say that, no, sorry, I cannot show it to you. But that's my point. Well,
I just gave you an example. The fact that you don't
you didn't.
believe me that
That's the
he
problem.
used gravity.
You're asserting something.
Okay, if you want to call it that, so be it. But basically, I don't really care. But yes, I am sure, I am 100% certain that he did use the gravity. And if you don't believe me that he did, you can just check with him.
Oh man. So you cannot show it, but I should go out and ask him. Okay.
Because you're the one interested, so I really don't care.
Obviously you don't.
I just know that in a project like that you basically have to take gravity into account, and if you want to get precise calculations, you need to at least use the small g. And
how
if not,
do you know that in the first place? Okay.
Because if I wanted to predict the trajectory of something that is affected by gravity, I need to include gravity in the calculations. No other way.
Yeah, sure. And that's what he did, you know exactly, without showing us in any way. Okay. So let's move on, because you're not gonna show anything, that's fucking sure. I'm sure about that, by the way. So the basic idea was that if you are using the gravitational acceleration, the Newtonian gravitational acceleration formula for anything, then you are asserting that the reality that you are using it for only includes two masses having a certain distance towards in between each other, and nothing else, basically. No other force,
which is not
no other
true.
masses, no other quarks or whatsoever. Quantum physics is not included whatsoever.
What
you
just stated
that's
is
reality. Even when you said 20 minutes ago that you are not calculating reality. You said it. You can listen back to it, by the way.
What you just said is basically equivalent to saying that when I calculate the volume of an aquarium, then I'm asserting that only the aquarium exists in reality, because otherwise I wouldn't be able to calculate its volume. And that's just plain silly.
No, nothing affects the volume of an aquarium besides itself. When I have masses, there are different effects on it that we do.
For example, temperature
exist,
affects the volume of the aquarium, because there is something like thermal expansion of the material. So then you have different volume of the aquarium in different temperatures.
Yeah, but we don't want to fill it perfectly in the first place.
Yeah, that's the point. You never need complete perfection. You need some kind of accuracy, and then you do calculations up to this accuracy, because you don't need more. If you can do more,
that kind of precision, then how could I predict anything regarding an eclipse? Based on those kind of formulas, how could I ever predict an eclipse down to the millisecond?
Because it turns out that the most significant effect in this case is gravity. There are, of course, different effects, like there is electromagnetism, there is, I don't know, solar wind, which exerts some kind of a force on basically every celestial body in the solar system, but it's just negligible. And if you take into account all the factors that turn out not to be negligible, then you can predict down to the second.
Do you know what was the first idea when someone introduced the problem, the three-body problem that was describing exactly what you are trying to say, by the way, like celestial body movements, right? They were trying to describe, especially, by the way, in the first place, the Newtonian gravitational formula exists purely because of the planetary movements, nothing else. No one came up with that kind of idea to have a formula regarding a force in between two masses anywhere else.
Yep, that's right? Probably true, but
well, if you know the history, because you were talking about history, not me, in the first place, but you should know this. And the first problem that they introduced to all of the problematic field of the gravitational force and the acceleration, that are in between different masses, is that what do you do when you have three masses?
Sure.
And what do you do? Do you know what the answer was to that question? What do you do?
Yeah, basically, it depends on the exact case that you want to solve. But in most cases, you basically, well, for example, I think one of the first applications of that was to describe the orbit of the moon, because in the motion of the moon, the sun turns out to be quite significant.
Orbit of the moon and the sun and the earth in between each other.
Yeah.
That
for example.
is the precise phrasing. No, that was the first one. So you're almost right, but okay. Yeah.
Yep. So in such a case, you're basically doing the and now what it's called in English again, the issue, but it's probably something like perturbation calculus or perturbation theory, which basically means that you describe the motion of a body like the moon as affected only by a single other body like the Earth, and then
so what do you
add perturbations on top of that.
What is the first thing that you
approximate?
No.
Solve a two-body problem, for example.
The first thing you do regarding a three-body problem and how will they have an any kind of movements towards each other regarding the gravitational acceleration theory altogether is that you rule out one out of the three. That's what you do.
If you want to do
like
this analytically, yes.
Even exist.
If you are solving analytically, then that's one of the methods, yes.
No, that was the first method. That was the first attempt to have a non-three-body problem after they introduced the three-body problem.
Okay, yeah.
And what did I write to you? Like now for more than an hour ago. Do you remember?
But that's... yeah, I know what you're referring to. But as I said, that's basically what... Okay, that's what you do. You solve a part of the problem, and then you try to approximate more and more the solution to the whole problem, if the whole problem from the start is intractable.
Yeah,
that's
you are kind of right.
Just one of the techniques.
So the technique is when you are presented with three bodies, then you act like there is only two. That's the solution.
One of them, yes. But if you're doing numerical calculations,
do you get
for example, you don't have to do that.
Do you get the paradox within that?
That's not a paradox. You know that there is some kind of...
If there are, let's say, 5 people coming at me on a train because they want to, have a go at me. Like literally, they want to beat you up, for example. Then you will act as if only one is coming towards you, or what?
But
Can you
that
do that?
In the end, they do not act as if the other body doesn't exist, but they just add it as a perturbation, because the influence of it is much smaller.
Then what?
What I mean is... then they can add influences of other bodies if they want to, because that's also possible. I mean, everybody knows that the initial solution when you are solving the two-body problem is not the final solution, because it doesn't take into account many of the factors. But that's just a way of splitting up the problem into parts that are solvable each on its own. Okay, so that's just because that it is known for a long time now. I'm not sure who proved it. Who proved it as the first one. But if you just write the equations of motion of more than two bodies under gravity, then you don't have a fully analytical solution, a closed form solution, as was written in the text that you quoted.
Yeah.
So you can't just write a single equation that you substitute the time into that equation and it gives you the positions of all the bodies. It's impossible. But what is possible is approximating it using various techniques and basically the perturbation theory is one of them. So instead of writing a formula that will give you the positions of all of the bodies, you are writing a formula that will give you an approximate position and then a better approximation and the better approximation, and the more steps you take, then the better approximation you will get.
That's not true. You write down one how should I put it? One group of calculations regarding what would happen in between two masses, and then you equate that as if it was a movement of one body, and then you superimpose that on the third body. That's what you actually
Not
do.
quite.
Oh my god, yeah, quite. Like very vaguely saying, so that everybody understands, that's what you do. You calculate what happens in between two objects, and then you superimpose that, whatever you come up with, on the third one. But that's paradoxical because in the first place we know because of the formula, because that's what the formula says, that's what the theory says, that any two masses will have an effect on each other. So when we are talking about three bodies, then how many effects we are talking about?
What you just described actually will give you a wrong result. I mean, correct up to some accuracy, but if you want to, for example,
you
predict
said that
eclipses,
you
it's
don't
far from enough.
you don't calculate anything exactly ever, so you should give me that, by the way. But again, how many different effects do you have when you are starting out with three bodies? Only three, by the way.
What do you mean by different effects? If you want
how
to...
many gravitational vectors could you write up on a simple model that you are drawing for yourself regarding those three bodies?
Okay, I'm not sure. I'm still not sure if that's what you're asking about, but basically for every body you will have two different forces from two of the other bodies.
So, how much is that?
I guess if that's what you're asking about, then 6. 2 per every one of the three bodies.
Yeah, exactly. I asked for vectors. Like, you talked to Bevo about it the very first, 10 minutes you were in, right?
Okay.
And you certainly do know. I know that you do know
right?
that any force is a vector. And I asked you how many vectors could you draw up as a little model that you are trying to represent the three-body problem with. Right? So that's 6. Yeah, you're right about that. That's 6.
Yeah, but
and
then
yet
you
are
can, if you want,
calculating for how many?
What do you mean? For how many? Basically,
For
you're adding
2.
the vectors and
You're
then you're
calculating when you are calculating with the gravitational acceleration force. You're calculating for 2, one to the other.
As
and
an
then
initial
back,
step,
right?
maybe.
Yeah.
As an initial, but then you're basically adding the influence of the other
so
body.
you're not calculating. That's the paradox right there, because there is a third body which would altogether give you 4 more vectors.
Okay, but
at the same time, because they exist in the same time, right? You're calculating as if one of them doesn't exist up until you calculated your first part. that's the
but
paradox.
then you modify that. But the problem is then you modify that calculation in order to take into account that you are actually adding more influence. But as I said, that's only one of the techniques, because if you're doing numerical calculations, you don't do all that. You're basically taking all the forces into account at once.
And which body will move first?
All of them at the same time. You don't do any moving first or whatever. Yeah.
That's great.
Basically, what you're doing in numerical calculations is you describe the state of the system as a position and velocity for every body. So you have, for example, if you have 3 bodies like Sun, Earth, and Moon, for example, you have 3 positions and 3 velocities. And then at every step of the simulation, you are calculating all the forces between all of the bodies. And for every body, for each body, you are basically calculating the total force. You are summing all the vectors, and you have the total force. And then
the total force of
you
what?
shift
Sorry.
the total gravitational force from all the other bodies acting upon this body.
How is that the total? Well, that's what I'm asking, because I think you slipped up there. What the total of what?
Of all the vectors, the sum of the vectors. Vector sum of all the forces.
Why would I need the sum of all the vectors all together? Summed up.
Because that's basically the total force that is acting upon the single body.
Oh, you mean that way? Also, from looking from one mass, how many vectors does it have to it and from it? Okay.
Yeah. Okay. So for each mass, basically you are taking all the forces that are acting upon it, and you are summing them to get a single force vector for every mass.
Yeah, and that kind of simulation starts with what assumption?
What do you mean?
That kind of simulation starts with what kind of assumption?
Well, you tell me, because I'm not sure what you're asking about.
Well, it starts with the three body being at a certain position towards each other. Yeah.
Okay.
So when you are trying to describe the celestial body's movement, how do you know that that was the original or initiate position in between them?
From observations.
What, you were there 4.5 billion years ago, even when
but you don't
the Earth
have
was
to
just
be
forming, or what do you mean?
But you don't need to start from there. You can start from any arbitrary point in time. Like, for example, you could measure the positions of the celestial bodies today, and then use that as an initial state of the simulation, and then simulate it however far away you want into the future.
I get your point, but do you know how many different arcs and then other different paths I can show to you or draw to you when I only know a certain amount of that arc? Because that's what we have as an observation.
I'm again not sure.
Right? So we only have a certain arcs of different paths of different celestial bodies. We only have certain movements that we see in the sky, right?
Okay, let's say.
Just part of the movement that we are assuming that before that movement that we actually observed, before that, it was acting this and this and this way. So therefore it will act in the future this and this and this way. When in reality, you can literally draw up an infinite amount of different paths that would match that segment that we actually observed.
That's actually true.
So how do you know which one is the real one?
Because that's, well, we don't know until we actually observe it, but the theory predicts a single one. A theory predicts some concrete path, and then we observe, and then it turns out that it actually matches the prediction. How about that?
Up until a certain moment it matches it. Like we are talking about, like, I don't know, 500 years.
Something like that, because it's basically very hard to measure the current positions and velocities with enough accuracy so that the calculations will carry out further in the future. Yeah.
So what kind of an actual path we are looking at? If we will draw up it like on a piece of A4 paper, we will draw up the motions of the celestial bodies. What kind of length do we have when we only observed? And we didn't, by the way, but let's call it from the beginning, whenever anybody talked about it, 500 years. What is that percentage towards what we assume to be the age of the universe?
Very small.
So how many different kind of paths I could draw up to you that would match that very small segment with what we observe?
Obviously a lot.
So how do you know which one is true?
Then, okay, now are you asking about the past or about the future? Because about the future you never know, and about the past you actually
don't know.
Also don't.
You just said you were
really
predicting eclipses based on what you think is reality. Like literally the gravitational forces. So how do you do that again? You don't.
No, you do. You predict them. Of course, you will never know with 100% certainty that it will come true, but so far, it just works.
You predict them the same way?
Yeah.
As they did way before any kind of physics field as a science field ever existed. So
I think we are not talking about the same thing now.
Then what kind of predictions are you talking about?
Basically the positions and velocities for almost any point in time. Well, any within some time interval for which we can expect reasonable accuracy.
Yeah, that's, for example, that's an eclipse.
Yeah, for example, an eclipse, yeah.
Then how are we not talking about the same thing? I don't get it. Okay.
Because I'm not sure what you're referring to. It's a bit chaotic.
I just explained 2 seconds ago.
In any case, yep, you can use this to predict eclipses, which I actually did. I didn't get as good accuracy as as
and to
the
that
actual
I
people
said
who are doing it.
half a minute ago that they did predict eclipses way before any kind of Newtonian theory of gravity.
Yes, they did, and they didn't, and they weren't able to get the same kind of accuracy we are able to get now.
Okay.
Nor were they able to predict the exact location where the eclipse would be visible.
By the way, I want to recap. Did you understand the paradox within the solution, or at least your solution to the three-body problem regarding gravitational force? Do you get my point?
Not really, because I don't think there is a paradox.
You don't have to agree with it. I'm not telling you that, and I'm not asking for that. I'm just asking if you understood my viewpoint of that regarding why would I call that a paradox.
No, not really, and I'm not even sure what you call a paradox right now.
Well, you have three-body problem, and you are trying to act as if only two bodies were existing. When you start out with the problem having three bodies, that's the paradox within the solution for the three-body problem, for me. That's the paradox, that you are presented with a problem, and you are acting that the problem is actually not the problem.
Okay, I don't see it as a paradox, because basically that's a common technique to start with a bigger problem and reduce it to smaller parts that are solvable. Basically, divide the problem into steps where you can solve every step at a time, and then arrive at a final solution that you have reasons to think that it will be a good approximation to the solution to the initial problem.
Okay, that's not what you do when you are trying to find a solution for the three-body problem. You yourself said that you are ruling out the third body. Because you call it negligible.
Initially, that's
so you are not compartmentalizing. You are not compartmentalizing the problem. You are just ruling out. That's the paradox. I get that you don't want to hear that, but that's the paradox itself. And you said it, by the way.
But do you understand that it is only initially, that you just do it to get some kind of a basis solution, and then you actually add perturbations to that solution?
By the way. You seem not to get the three-body problem in the first place. That's what the three-body problem is about. And you are not compartmentalizing it. You are acting as if the initial state of the three bodies were actually not the initial state of the three bodies. That's the paradox. When you are coming up with a solution like that.
As an initial step. You're still ignoring the fact that there are more steps after that, which basically kind of return to the fact that, okay, we have some kind of solution, but it's not a solution to the initial problem. It's a solution to a different problem. And now we want to add modifications to it so that it will become a solution to the initial problem. And then we are getting something which is actually a solution to the initial problem. Well, approximate solution, but still a much better solution than just the one that we get from the first step, where we ignored the third body altogether.
Yeah, ignored. That's the main thing you have to get into your mind when you are talking about your believed scientific field having a solution, which is actually not a solution, but it's a solution for another kind of problem because it has a different kind of initial state.
Nope.
Than the actual problem having.
Okay.
That's a problem in itself. That's the paradox.
Okay. Let me put it this way. When you calculate perturbations, you're basically generating a sequence of solutions. And the first solution of this sequence is truly a solution of a different problem, just as you are saying, because basically it's the solution to the two-body problem, and that is true. But it's the first solution in the sequence, and then every next solution in the sequence adds some perturbations to the previous solution in the sequence. So then you have basically multiple steps, and you can do as many as necessary to get the desired accuracy, where every next step adds something to the previous step and modifies it, and basically generates a next solution and the next solution and the next solution. And basically the further you go in that sequence, so let's say S0 is the initial solution for the two-body problem, then S1 is S0 with some perturbations, then S2 is S1 with some perturbations, etc.
Three bodies.
Yeah, you have three
That's the
bodies, but you can
paradox.
still...
I cannot
dear.
phrase it in any other way that I tried to already. Like I tried it with 4 different things, I think.
And you're still not understanding the kind of the crux of how this works.
I explained it myself.
Yeah, you explained the first step, but you have literally no idea about the next steps. That's what I get
Yes,
from
I
the
did
conversation.
explain that. Very vaguely, of course, but I did explain it.
Yeah, and basically what you did explain is not actually a solution to the three-body problem, or at least not the solution that you can
I said
get to the
that you
three-body
act like
problem.
if you only had 2 bodies, then you come up with a within that kind of little system that you created out of reality, because you have 3 bodies actually. So you created a true 2-body problem that doesn't exist, because we don't have 2 bodies, we have 3 bodies. That's why it's called a 3-body problem again. You come up with an idea to have a 2-body problem, you get a conclusion from that, and that you impose on the 3rd body. That's what I said, and
Yeah,
that's
and
what
that
you
is
just described also. So how did I didn't
not
understand it?
quite. Because the problem is that you don't understand that in the step that you describe as imposing a solution on the third body, it's not what you are describing, because what I understand from what you are describing is that you think that you basically take this unchanged and you put it in the context of the third body, and for example you take Earth and the Moon orbiting as if they are a single body, and then you put it on the orbit around the Sun as if they are a single body. Is that what you think is going on?
Something like that, not exactly, but something like very vaguely saying, yeah.
Yeah, but the problem is it's not quite what happens. I mean, it can be thought of as a
That's
next
why I said
approximation
very
or something
vaguely.
like that. But then what you do is you also calculate perturbations from the Sun acting on the Earth and the Moon, and you add these
Sorry,
perturbations
how
to
do you
the
do that
motion
if
of the
your
Moon
first solution
of the
was
Earth.
to active only 2 bodies existed? How do you do that now after you already have one? Then now you're doing it for the 3 altogether. No, you don't do that. It's
You
not how
actually
it's
do
done.
that, and
No.
you can do that thanks to the fact that the Newtonian gravity is a linear theory, which means you can add solutions to each other.
Yeah, you can
So
add
you
solutions
can.
anytime you want, in anything, especially mathematics. Anytime you want. You can do that within mathematics. It's still not gonna represent reality.
And funnily enough, it does actually, because if you do calculations
Yeah,
this way,
because
they do
you
fit
went
reality.
out to space and you saw how actually the 3 bodies are moving. Specifically saying the Sun and the Moon and the Earth are moving.
Okay.
That's how you know that it exists, right?
We kind of did, but that's not even important right now, because you can just observe the Moon
No,
and
it's very important.
where it appears on the sky.
Because
No,
you just
it's enough to just watch.
implied that you know that it works, which means that you should have gone out and you checked it.
Okay. By it works, I mean what the predictions regarding observable values from the theory match the actual observed values from reality. And then the question is what the
What is the
observable
observed
values
reality
are,
regarding
because
that? That's what I'm asking
for example, the positions of the Sun and the Moon in the sky.
In the sky.
That's enough.
That was also
Yes.
established way before probably the eclipses themselves. Like, what do you
Yeah,
mean?
they had some models, but the models were quickly losing accuracy in time. They didn't have
Really?
the kind of accuracy we
The
have right
Mayan
now.
calendar was wrong as fuck for I don't know how many thousands of years, right? Wow. I never heard that one before. Because from a physics point it should be wrong. But from another one, like let's say archaeology, it's fucking great. So which one do I believe?
And what did the Mayan calendar contain exactly? Did it contain the exact
Oh, but
positions of the
please look
Sun
it
and
up.
the
I
Moon?
cannot give you like I don't know how many different lectures within 1 hour or 2 hours. So please
So
look
you
it
think
up.
you're giving me lectures?
Please look it up.
Okay, but yeah, I definitely will take a look, and yeah, we'll see. All right.
Well, okay, I guess we would go in circles if we would continue this, by the way. Right?
Yeah, probably. Okay, so yeah,
Great.
so thanks.
That's probably
thanks for
the
the conversation
second thing
and
that we agree on, by the way. At least something.
yeah, let's say.
Okay.
Yeah. All right.
Okay, well,
Yeah,
whatever it means to you, thank you for the conversation.
thanks, and yeah, maybe talk to you another time.
Yeah.